Hello everyone, welcome to the Electromechanical Devices course. In today's lecture, we're going to continue the chapter 3, which we have started the previous meetings. We discussed in the previous videos, our meetings, we discussed the capacitors and capacitance, and we went over the operating principle of this electrical element and how we can relate, or what is the relation between the voltage and the current over this electrical element, the capacitors. In addition, how we can calculate the power, the energy stored by a capacitor. So we discuss all of these different things. In addition, we discuss the how we can calculate or come up with the equivalent capacitance of set of capacitors that are arranged in parallel or in series. So today we're going to continue the chapter, and this is going to be the last part of chapter 3. And the next meeting we shall be moving to the chapter 4. So in today's lecture we're going to discuss the inductors and inductance. Again, this is another electrical element that would be used for controlling the voltage and the current through the different electrical elements or through the electrical circuits. And we said that the capacitors, inductors, and resistors, basically they could be considered like controllers. Like they give us the ability to control the flow of the current and the deviation or the change of the voltage through the electrical circuit. So they give us this kind of ability. So in terms of design of the electrical circuit, we are using them a lot. But again, the objective of this course is to give you these keywords and these concepts of the electrical or electricity and electrical circuits, and the objective again is to do analysis for electrical circuits. So we won't gonna do through the design, but we shall be studying how we can do analysis for electrical circuit. This is the main objective of this course. So in this part we're gonna discuss again the inductors and inductance. So inductance, it is the energy, the electric energy that accounts for the energy stored by a magnetic field or in a magnetic field. If you compare the inductance to the capacitance that we discussed in the previous meeting, we said that the capacitance is electrical energy or electrical property that accounts for the energy stored in electric field. In case that we do have an electric field, how much, and we would like to store this electric field. Again, the electric field is like like kind of a force. Like you have an electric force, and any force, it will be converted into energy, right? Or required energy to be generated. So here the capacitance, it is the store of the energy, and this energy should be electric energy that comes due to electric field. But the inductance or the inductor, it restores energy that would be generated due to magnetic field. So there is relation here between the energy or the electric energy or electricity and the magnetism that should be considered through the inductance. Also, we said that for the resistors, that the voltage through the resistor, it is proportionally related to the current. And also for the capacitor, that the voltage is proportionally related to the time integral of the current. But for the inductor, and this is what I'm gonna show you right now, that the inductor is proportional, its voltage or the voltage across the inductor is proportional related to the time derivative of the current. So as you can see, we can give like a summary right now that the voltage is proportional related to the current in case that we do have resistor. And for the case of the capacitor, the voltage is proportional to the integration of the current over time. But for the case of the inductor, and this is what we're going to discuss today, that the voltage should be proportional to the derivative of the, directly proportional to the derivative of the current with respect to the time, or with respect to the time, as I said. So these are the three controllers that we are interested in. In chapter 2, we discussed the resistors, and we have practiced and know how we can do analysis for electrical circuit that include resistors only. And through chapter 3, we are discussing the capacitance and the inductance, or the capacitor and inductors as already given, and we end up with these two relations, right? That gives us ability to control more the voltage and the current and their relation together. So Inductors are, this is like a conventional, like this is a schematic how the conductor is gonna look like if we open any one of the inductors generally. Like the inductor or the concept of the inductance, it depends on using or coiling a wire around magnetic material. Magnetic material that it would be like iron oxides. These are most common types of magnetic material. A magnetic material that the material that can allow for the generation of magnetic fields. Like iron, as I said, or iron oxide, like the magnet, the iron can be attracted to a magnet. So we're gonna say that this is a magnetic material, and the most common type of a magnetic material is the iron for sure. So that's why iron and iron oxides are the most common material that would be used for making inductors. And the concept or the structure of this inductor is very simple, that it depends, as I said, on coiling a wire around a magnetic material like the iron. So inductors are constructed by coiling a wire around some type of the form. All of these are different forms of the inductors, or the how we gonna form kind of the magnetic material. The coil form, which is, this is like a coil form, this is a form, this is another form. So it's composed of a magnetic material that increases. It's composed of a magnetic material, and the objective of this magnetic material is to give increase in the magnetic flux for a given current. So what happened basically when there is a current flow through the wire, there should be some magnetic field that should be generated, but this mainly depends on the type of material that we're already coiling the wire around. If we're already coiling the wire around an iron material, so the magnetic field, it shall be increasing and it will be significant, it will be clear. But if we are using like in magnetic material, or the material with very low magnetism, or magnetism ability, you could say that in this case we're gonna say that this material, or barely we're gonna see or find any magnetic field or flux that is gonna be shown up on the flow of the current through the wire. So the key idea that we should have a conductive wire that is made of a conductive material, and there should be a current flowing through the wire, and this wire should be coiled around a magnetic material like iron, for example, as I said, and it would take different forms as represented here. Okay, and but if you compare this form or this structure of the inductor to the structure of the capacitor, we said that it is composed of two plates and there is a dielectric material in between them, right? Here we do have the coil that is already coiled around, or the wire coiled around a magnetic material. So inductors, and how about their operating principle? In the capacitor, for example, the operating principle that there was like two plates, and there was like a dielectric material that insulate the area or the region between the two plates, and there should be some flux or some flow of electrons that is going to be trapped between the two plates of the capacitors, and this will result in some difference in the charges over the two plates, and this difference, it will result in some electric field that will be stored. Then it can be used once this electric field that continue to accumulate, it builds up at a certain level, it will be allow or let for the electrons to flow through the dielectric material. And in this case, we store for a while, then we can use the electric energy after that. This is the concept or the operating principle of the capacitor. How about the operating principle of the inductor? The inductor, it works, as I said, that there should be a battery. This is like the source. This is like battery here. For this case, this is like the battery, right? Or the source, the voltage source, Vs, and there should be current. So you could consider this is like a very simple electrical circuit, and send the current already, as long as the current flow through the coils, or the you could say that the wire that is already coiled around the magnetic material will result in some magnetic field that will be generated as already represented in this schematic. So when current flows through the coil, a magnetic field or flux is generating. Again, the magnetic field, it is like kind of a force or kind of energy that is going to be magnetic energy that is going to be generated around these coils. Thus, current creates, you could consider that, we can say that the current creates electromagnetic field, and this is what fits with the Faraday's law of magnetic flux. Like when we have a current that is changing, and the key idea here that the current should be changing over time, there will be a magnetic field that it changes around the coil as well, and this magnetic field change will result in some voltage change. Voltage, again, as we mentioned before, it is energy. It is kind of energy. This is the electric energy, right? So since we have a voltage difference between the ends, like here, and that's why you have a battery, the battery is going to give a volt and is going to deliver a current. This current is going to keep flowing through these different coils and will be returning back again as it is. But because of the magnetic field, the voltage or the electric energy here, it will be different than there. So we're going to end up with some voltage drop or voltage difference. This is the volt, which is just energy or difference in the energy between the two ends of the coil. So the change in the electromagnetic field will result in some, or induce it will produce some voltage across the voltage drop or energy change across the ends of the coil in a direction that is anti-parallel to the current. So we're going to end up at the end, according to the Faraday's law, that the voltage that across the inductor, this is the inductor, it should be proportional according to this Faraday's law, that the voltage across the inductor should be proportional to the time derivative of the current, or the derivative of the current with the time, or in other words, to the change of the current through the over time. So what does it mean? It means that if in case that we don't have a change, if there is no change of the current over time, there is no magnetic field will be generated, or there is no change. In other words, the magnetic field will be generated, but the change in the electromagnetic field will not be generated, and there is no voltage. So it works in this way. Like we should have a change in the current over time. That's why we do have di by dt. This is the change of the current. Di by dt, this indicates a change in the current. All right. So what happened then? This change of the current will result in some change in the electromagnetic field. If the electromagnetic field does not change, there is no volt. But if the electromagnetic field changes, so there will be volt that will be produced. It means that we do have a change or difference in the magnetic field, that will be generated due to the current flow. And because the current changes, this magnetic field will change, which will result in some difference in the energy at this point than the energy at this point. Right? So this difference in the energy is known as the voltage difference. And if you remember that we define the voltage as electric energy. This is the energy itself, right? So since we're going to end up with some difference in the energies at the two ends of the coil, this will result in some voltage. But this definitely requires a change in the current. If there is no change in the current, there is no volt. And this is simply already observed here. So the constant of the proportional relation is commonly known by L. This L is known as the inductance of the inductor, right? So this is the inductor, and this is the inductance, which is a measure of the inductance of this inductor itself, which is dependent for sure on the magnetic field and the material type of the magnetic material that this coil already surrounding it, in addition to the amount of current through this one. So the L is the inductance, which is measured in henries, and henries, which is H, this is the henries. H is equivalent to the volt times second divided by ampere. A stands for the ampere, S stands for seconds, and V stands for the volts. So, and this is the measure again, or the unit, the henries, or the measure, the inductance of the inductor, of the inductance of an inductor that relate the volt to the current. Again, in case that the current is constant over time, it means that in case that we do have DC current, so there would be no voltage that shall be generated. So the volt will be in this case 0 in case that the current is already constant over time. If we compare this expression to the case of the capacitor to work, this is what we discussed in the previous meeting. The capacitor to work, it requires a change in the voltage over time. To give so the capacitor works like it stores energy, right? And this thing also the inductor, it store energy, but due to magnetic field, right? So the capacitor, it stores energy that depend on a change in the voltage. Or the concept of the capacitor, it depends mainly, or it works as long as there is a change in the voltage. But here the inductor, it works as long as there is a change in the current over time. Make sense? This is the difference between the two electrical elements. So this is the expression that we discussed above, right? That the voltage is L times di by dt. And so this is the volt in terms of the current. How about if we would like to end up with the current in terms of the volt? So definitely if you integrate both sides, we're going to end up with this expression. This is the current in terms of the volt, in case that the volt is the one that is given as a function of time. So you are going to integrate this volt as a function of time from t0 to t, where t0, this is the initial instant of time that you already started studying the inductance or the current through this inductor. Divided times 1 over L, which L is the inductance of the inductor that should be measured in henries, as I mentioned, plus I of t, 0, which could be written as I0. This is the initial current that through the coils of the inductor itself, right? In many of the cases, I0 we're gonna consider it as 0. So I0 will be considered 0 in many of the cases. So we're gonna end up with the simple expression that it will be 1 over L, the integration from 0 to t v of t dt, right? As I'm gonna show you an example on this expression. So as you can see that you're gonna find that this inductor is completely the opposite to the capacitor. The capacitor, its voltage, it depends on the integral of the current, or proportional to the integral of the current, and the current is proportional to the derivative of the volt. This is for the case of the capacitor. But for the inductor, it is the opposite. The voltage, it is proportional to the time derivative of the current, and the current is proportional to the time integral of the voltage. Right? How about the stored energy and the power? The power is very simple as usual. The power all the time through any electrical element is the voltage over or across this element times the current across this element. So if in case that we do have a coil and the voltage over this coil is just V of t, and the current through this coil will be I of t, so definitely the power that the electric power of this coil or through or across this coil will be V times I. And we define the I as the integral of the voltage, or we define the volt as the derivative of the current. So if we remove the volt and we substitute with the current, we're gonna end up with this expression for the electric power through the coil. How about the energy? The energy, this is the electric energy. The energy is the time integral of the power over the electrical element, or how, because there is a power and this is the energy stored by this electric energy. So if we integrate the power over time, this should give us the energy definitely, and the power should be measured in watts, and the energy should be measured in joule. And if you remember that the watt should be joule over second, so that's why we do the integration here. If we did the integration of the power and we substituted the power, which is L times I times di by dt, and we did integration, we're gonna end up that simply because we can cancel, we can get to remove this dt with the dt, so we're gonna end up with the integration over the current, not over the time. So that's why we're gonna change the limits of the integral from time to current. So we're gonna end up from 0 to I, Li di. This definitely is gonna give us, this integral is gonna give us Li square over t, as long as the L is already constant with respect to the current. It means that in case that we're already using a material that does not depend on the current, so this inductance will be constant. So we're gonna end up with I square over 2, which is gonna give us this expression for the electric energy over the inductor. Make sense? So these are the expressions. If you try to compare these expressions to the ones of the voltage in terms of the current in terms of the volt, the power, and the energy, for the capacitor to the resistor to the inductors, we can compare them. So we're going to end up with some different expression that you have to memorize them and know the difference between these different element, electrical element in terms of these expressions and how they relate the current to the volt. So now let us consider this example, which is typically the same thing that we already did before for the capacitor. We're gonna do here for the inductor, but we're gonna use these new expressions. All right. So for this one, it is given that this is the current as a function of time. In this plot or this graph, the current is given as a function of time, and the time is already given in seconds, and the current is already given in amperes, as already given here. And the current through 5 Henry's inductance is shown in the figure. It is required to plot the voltage, the power, and energy through this inductor. Like, assume that we do have this inductor with inductance L equals 5 Henry's as already given up there. And this is the current. There is a current through this inductor. This current changes over time. Again, if the current does not change over the time, there is no voltage. So there is a change of the current over the time as already given here. And we are interested to find the voltage, how much it is, the power, how much it is, and the energy, W of T, how much it is over this inductor. So it is very simple. It's gonna be the same thing that we did before for the capacitor. We're gonna repeat the same concept for a similar example for the inductor here. So, but we have to come up or write the expressions. How much of the volt in terms of the current, how much of the power in terms of the current, the same thing for the energy, right? So going back to this expression, the volt as given here, it should be L times di by dt, the derivative of the current, and the power, it should be V times I, and the energy, it should be the integration of the power over the time, right? So it means that V of T, it should be L times the di of T by dt. This is the first expression. The second one, that the power, the electric power directly, we can find it. If we found the voltage, we can multiply the voltage function times the current function. We're going to end up with the electric power very quick, which is going to be the simplest form. Then if we did integration of the power over time, this definitely is going to give us the energy, dt. And if you remember in the previous example, in the previous video for the capacitor, we said that for the energy calculation, since we are interested in plotting, it is required to plot, to draw how the energy changes over time. So don't block the limits of the integration. Just do the integration of the power over time, and that's it. There is no limits. But if we are interested in the calculation of the overall or the total energy stored within this period of time, so in this case, we have to block the limits of the integration, or we can plot the figure of the energy. Then we can calculate the area underneath or below the curve to end up with the total energy, as we discussed for the capacitor in the previous meeting. So we're gonna do the same, but we just gonna use different expressions. So to find the volt, the power, and energy, definitely we should come up with the discrete function of this figure of the current, right? So as you can see, as usual, this one is gonna be split or divided into 3 time periods, starting from the 0 up to 2 seconds, then 2 to 4, and 4 to 5. And as already given here, this is a linear function, so we have to write this linear function. We can calculate like delta I and delta T, because the vertical axis is I, so we're gonna find delta I, and the horizontal axis is delta T. Delta T here is just 2, delta I is just 3 amperes. So this is gonna give us the slope. The slope should be delta I over delta T. So if I ask you to write the equation I of T from the discrete equation or function of this graph, within this first time period, we do have a slope of 3 over 2, right? Because delta I is 3, delta T is 2, so it's gonna be 3 over 2, this is the slope. And this slope should be positive because it moves between the first and the third quadrant. It means that this line it has a positive slope, and the horizontal axis is already the x-axis is already the time, plus b0. B in this case, it should be 0. Why 0? Because the intersection of this line, or this line will intersect with the y-axis or the i-axis at 0. It means that the y-intercept of this line, it should be 0. So it should be plus b, and b is already 0. This is within the time range between 0 up to 2 seconds. How about the second period? There is a constant function with the current equals to 3, and there is no time here within the time period between 2 to 4, and between 4 and 5 we're gonna end up with a declining or decreasing slope. It means that this slope should be negative, so we're gonna have a negative slope of this function. With this function, it will have the slope can be calculated as delta I and delta t. Delta t in this case is gonna be just 1 because the time difference here is just 1, and delta I it will be 3 as well. So we're gonna end up with a slope as negative 3, and the time plus b. How much is b? B it should be calculated the simplest way as usually, just to plug t equals 5 into this equation, where you should end up that the current it should be 0 here. So if we substituted for this equation for t, the current at t equals 5, it should be 0, which should give us the negative 3 times 5, because the time it will be 5 plus b. So how much is b? B we're gonna end up that it should be 15. So it means that we can simply substitute for b into this expression. We can remove the b and we can use the current, the b should be 15 in this case. So it's gonna be plus 15. Make sense? We can even write this equation in by considering the 3 as a common factor, so it will be in another form. But anyway, just leave it in this form for now, and this should be within the time period between 4 and 5. Make sense? So we got the current. Simply we're gonna do derivative to the current to end up with a function for the voltage. So the voltage function V of t, it should be the L, which it should be the inductance, which is already given by 5 henries. So you're gonna multiply times 5, but after you do time derivative to these expressions. So what I'm gonna do here, the derivative of this term, it should give us with respect to the time, gives us 1.5, which is 3 over 2, times 5, which is the henries, the inductors, times 3, 5 times 3 divided by 2. This gives us 7.5 volts. That should be within the time range between 0 to 2. And the second period, the time derivative of this one is just 0, so automatically the volt will be 0, and the derivative is 0. And the time derivative of this term gives us this term plus 15 will be 0, and the time derivative here gives negative 3. So negative 3 times 5 gives negative 15 volt. And this should be within the time period between 4 to 5, and this should be between the 2 to 4 time period. Make sense? So this is for the voltage function. The negative here of this volt, this indicates that this energy will be dissipated. Like again, this is like, it works like storing electric energy. Again, it works like a capacitor. But the capacitor to store energy requires change in the volt, but the inductor to store energy requires change in the current. And the energy, the electric energy, and what type of energy that the inductor generates, it is electromagnetic energy. What does it mean? It means that the energy that comes or produced due to the generation of a magnetic field upon the flow of current according to the Faraday law that we have discussed above. Make sense? So this is for the voltage. How about the power? The electric power, it should be the volt times the current. So simply you're gonna multiply all of this, like 7.5 times 3 over 2t, and 0 times 3, and negative 15 times this function to end up with the power. So simply we can find the power as 7.5 times 1.5. This is gonna give us 11.25 t. This should be within the time period between 0 to 2. And the second time period, if you multiply 0 times 3, this definitely gonna give us 0 power within the time period between 2 to 4. And for the third time period, negative 15 times this expression. So we're gonna have here the 15 times 3, it will be 45t, and the negative 15 times 15 gives us the 225. Make sense? Because you're gonna multiply negative times positive gives negative 15 times 15 is the 225, and this should be within the time period between 4 to 5. Make sense? Once we got the power, we can simply calculate the energy at the integration. Just integrate this function over the time, or all of these discrete functions over time, you're going to end up with the energy. So the energy W of t will be definitely the integration of these terms. So the integral of t gives t squared over 2. So this is going to give us the 11.25 divided by 2, which is going to give us the 5.625 t squared. And this should be within the time period between 0 to 2. And the second time period, the integral of this one, we said that is going to give us constant c. The integral of the 0 over time gives a constant value, because the derivative of the constant gives 0, as we explained in the previous video for the capacitor, and it's going to be typically the same. This should be within the time period between 2 and 4. And how much is this constant value? We're going to figure it out once we plot the energy function. All right, so now how about this third equation? This third function here, the 45t negative 225, it is so tricky actually. So because we are interested in finding the integration of the power, right? So this expression, all of it is just the power. So in the integration, it should be done over this one like a single term. So what does it mean if I ask you to find the integral of this term? So the correct thing that we have to say that the squared, it should be squared, the parentheses should be squared divided by 2 divided by the coefficient of the derivative of what is inside the parentheses, as we did before, right? So it should work in this way. You got my point? But basically, if you're just gonna look to the expression in this way and ask you to do the derivative of this function, so simply you're gonna say that the derivative of this function will be 45 t squared divided by 2, right? It will be t squared divided by 2 negative 225t, right? Simply, very simple. If I ask you to find the integral of this function, you're just gonna add t squared divided by 2, and you're gonna add t here, and this should be constant. And since we are not applying the integral limits, you aren't gonna add the constant, right? And this should be within the time period between 4 and 5, and you're gonna proceed. You got my point? But this won't gonna give a correct result at the end, unfortunately. Why? Because originally we are doing the integral of the power, all of this term in the power. Since we are not incorporating the integral limits, you should do the integral to the overall term as it is, like a single bracket, like a single parenthesis. The other option is just to consider that the power equals 1 over 2 Li square, and this is what it is recommended. It is recommended to consider that the energy, is 1 over 2 Li square, which we already got it from the integral of the power, but there are some constants that we didn't consider them in this function. It means that if you decided to work in this way, you should add here plus c and plus constant, and you should figure out to do some calculations to find this constant. You got my point? But the easiest way is to either to use this expression, or if you decided to work with the integral, of the power, the integral of the power, it should be over the overall parentheses. This is the thing that should be integrated. You got my point? This is how it works. So what I'm gonna do right now, I'm just gonna keep this one. I'm just gonna keep this term as it is. I'm just gonna keep this term, this integral as it is, and I'm gonna show you that this one, it won't gonna work, and you have to do the integral of the overall parentheses. You got my point? So, and now let us move. So what we did here, we got all of these three functions. We got the voltage, the power, and the energy as already required here. Then we're gonna move to the plot to plot these three functions as I'm gonna show you. All right. So for the first function, the voltage function, which is going to be a very simple function that we can draw here, the horizontal axis, definitely it's going to be the time, that it should be in seconds as already given up there. For the current, this should be in seconds. And the vertical axis is going to be the volt, V of t in terms of volts, right? This is the unit. And as you can see, all these functions are just constant functions. So this is, the voltage is a very simple function because the first function is just 7.5. So it means that, okay, let me just do changes here because I do have a negative here. So I'm just gonna move this t axis a little bit or to here, to have like, this is the time in terms of seconds, and this is should be the voltage axis, which is V of t in terms of volt, right? So we're gonna have here for the first time period between 0 to 2, so I have to split it into 0, and this is the 2, and this is the 4, and then I do have the time period 5. Within the time period from 0 to 2, I do have a constant function of 7.5, so this should be constant of a value 7.5. And then within the second time period, it should be 0. Between 2 to 4, it should be 0. Then the third time period, which is this one, it should be negative 15. So I should have here like negative up to negative 15 over this negative 15 here, right? Then simply you're gonna connect between all of these lines to have like a single curve, kind of, but this curve is just a discrete curve or representing a discrete function. So this should be the voltage plot and how it changes over the time. So as you can see, initially within the time period from 0 to 2, we have a positive volts. It means that we already storing energy due to the electromagnetic field, and that's why it is positive. Then within the second time period, there is no energy, there is no voltage. Why? Because the current was constant. The current is constant within the second time period here, so that's why we do have no voltage within this period. Then it's gonna be negative. It means that somehow we're gonna make use of this energy, or the direction of the voltage is gonna be converted, kind of, okay, through the electric. Now let us move to the power. The power function, it is, as you can see, it is a linear function. This is 11.25 t, and this is 45 t. Negative 225. So all of these are linear function except this one is just a constant function. So even the power function, it is very simple that we can plot this function as we did before in the previous meeting. So this is the time in terms of seconds, and this should be the power in terms of watts. This should be the unit of the power. And we do have three time periods, which are the from 0 to 2 to 4 and 4 to 5. For the first one, it's just a linear function. How we can draw a linear function? Simply, you're gonna locate some points and connect between them with a straight line, since all of these are linear function. It is very simple. So your objective is just to block t equals 0 once and t equals 2 once within this time period between 0 and 2. So if I substitute for t equals 0, we're gonna end up with 0. So this is gonna give us the first point. And substitute for t equals 2, this is gonna give us 11.25 times 2, which should give us 22.5. So when t equals 2, we're gonna end up with this value as 22.5 as power, as already represented here at this point. Then your objective is just to connect these 2 points together. So I'm just gonna connect them with this straight line between the 2 points. So this is gonna give us the first line or the first curve. Within this time period between 2 to 4, it should be 0. So there should be 0 here. So it should be dropped. There is a sudden drop in the power within the time period between 2 to 4. Then beyond the 4, it's gonna build up again, kind of. So your objective is just again block t equals to 4 into this expression. If we substitute for t equals to 4 times 45, negative 225, this is gonna give us negative. So we're gonna move to the negative down here. So this is gonna give us this point, and this point it should be next to the negative. This point it should be next to the negative 45, right? So this is gonna give us a point. If you substitute for t equals 0 into this expression, we're gonna end up with 0, right? Because 45 times 5 gives 225. If we substitute, we're gonna end up with 0. So this is gonna give us the second point. Simply, if we connected these 2 points with a straight line, why straight line? Because this is a linear function. We're gonna end up with the curve of the power. So this is gonna give us the curve in this way, right? Like as you can see, the power it builds initially. As long as we're already giving a voltage, it means that there is electric power that will be stored within this period there is no power, then this power will be used after a while, or this is not storing power, because we cannot store power, we can store energy. The thing that can be stored is energy. So to be more accurate, we're gonna say that to describe this figure or explain this figure, we're gonna say that within the time period between 0 to 2, the inductor delivers electric power, and within the time period between 2 to 4, there is no electric power through the inductor or by the inductor. But beyond this period between 4 and 5, this inductor, it takes power, or kind of like dissipate power, or uses or consumes power, kind of. So here now, let us move to the plot of the energy. So this is gonna be the vertical axis for the energy, for the W. And where the W should be in terms of joules, right? And the horizontal axis definitely is gonna be the time in terms of seconds. Again, we're gonna divide this one into 3 time period from 0 to 2, 2 to 4, and 4 to 5, as already given here. So within the first time period between 0 to 2, your objective is just to substitute for t equals 0, then 2 equals 2, you're gonna end up with 2 points, but then we have to connect these 2 points with a curve, not with a straight line. And this curve, it should be representing a quadratic function. As we discussed in the previous meeting, the quadratic function or the curve of a quadratic function, it would be open up or down depending on the coefficient of the t-squared term, right? So the coefficient here is positive, it means that it should be open up. The same thing here is positive, it means that it should be open up. And this is what we're gonna present here. So for this curve, for this point, if you plug t equals 0, we're gonna end up with 0 within the first period. T equals 2, we're gonna end up with 5.625 times 4. This is gonna give us 22.2. So the second period here, the second point that we're gonna get is 22.5, right? So we end up with these 2 points, and we have to connect them with a curve. This curve, it should be open up. To be open up, it should be curved in this way, because this is gonna give us like a U shape, and this U shape will be open up. So it means that the curve, it should be going down. Blue, the curve, as I'm presented here. So the second time period is just constant. For now, we have no clue how much is this constant. You can even, definitely it's gonna be the 22.5, because the energy curve, it should be continuous kind of, or it is not have this sudden drop in the power like we're gonna have here. But anyway, you can just skip this one for now and move directly to the third function. So now going back again to this function, to this expression, as we said above, that this one, it won't gonna give a correct result, as we mentioned. Why? Because we should do the integral to the overall term of the power, either to use the 1/2, the expression 1/2 L I square of t. This is recommended, as I mentioned, or you can simply do the integral of the overall term. So I'm gonna show you that in case that we plugged these data, these values here, if we substitute for t equals 4 and t equals 5, we won't gonna end up with a consistent result here with the curve, as I'm gonna show you. So for example, if we substitute t equals 4 here, we're gonna end up with 22.5 times 4 times 4, negative 225 times 4. This is gonna give us negative 540. So it should give us like a point that is very way here, right? And if you plug t equals 5, when t equals 5, this is gonna give us 25 times 22.5, negative 225 times 5. This is gonna give us negative 562.5. It means that you're just gonna end up with another point somewhere here, right? So we're gonna end up with a curve down here. And if you decided to connect this point to this point, these 2 points together, we're gonna end up with a curve, with a line. But this function, the energy function within the time period, it should be constant function, because this is a constant function, right? So it means that if we decided to connect these 2 points together, it means there is something wrong, right? It means that this function, it doesn't work for us. And this demonstrates what I said above. It means that we have to consider the integral of the overall of this one as a single parenthesis. Why? Because we didn't plug the limits of the integral. Or the other option, you can directly find the square of this function and multiply this function times 1 over 2L. Like you calculate 1 over 2Li square. So you're going to calculate the square of this function times 1 over 2. This is going to give the same correct result that I'm going to do right now. So if we decided to work with this one as a parenthesis, so this one it should be removed and replaced by the 45t negative 225 squared. This should be squared because you just, if I ask you to do the integral to this bracket, so you're gonna add a square and divide by the new exponent, which is 2, times the derivative of what is inside the parentheses. The derivative of what the parentheses, the bracket itself, it should be 45, right? The derivative of this term is just 45. This is gonna give us this function. This is the correct representation of this function as it should be represented in this way. Now, if you plug t equals 4 into this expression, just substitute for t equals 4. So 45 times 4 negative 225 squared divided by 2 divided by 45, this is going to give us 22.5. This is going to give us when t equals 4. So when t, let me use the green color, when t equals 4, we're going to end up with a point at the 22.5 as we got here, right? Then if you plug t equals 0, equals 5, I'm sorry, t equals 5, so this is going to give us 45 times 5, negative the 225, which is going to give us 0. This term will be 0 when t equals 5. It means that we're going to end up with a second point. As you can see, we're going to end up with a curve, and the curve should go down to have a U shape that is already open up. Right? So what does it mean? It means that this is going to be the curve, and if we connected these two curves, these 2 points together, we're going to end up with a constant function. It means that this constant function should be 22.5. So now the curve, it makes sense. Now the curve is correct. The function in the middle here, it should be constant function. So this is a very important note that you have to work with this term. If you decided to calculate the energy at the integral of the power, you should work with this term as a single bracket or a single parenthesis. So you're just gonna, or a single term. So you're gonna square all the parentheses and divide by the new exponent divided by the time the derivative of what is inside the parentheses. Make sense? So this is how it works, and this is how you do the integral. The other option, as I mentioned, is just to use the expression as 1 over 2 I square times L. Make sense? So we're going to end up here with the energy function that it should be plotted or represented as already given in this figure. Make sense? So this is for the energy and the 3 functions. And as you can see that the inductance, the energy over the inductor, it increases and it maintains constant for a while, then it will be dissipated, it will be consumed, since we already have the power is already negative here, right? So as you can see, all the figures are consistent together, and this is for this example on the inductor and the voltage and the power and energy over this. Now let us move to the last part of today's lecture, which is the inductances in parallel and series. How about if we do have set of inductors that are arranged in series, like in this case, or in parallel, like in this case? We said that what distinguish any electrical element that it should be arranged, or set of electrical elements that they are in series or parallel, that the series one, they should have the same current, or the current over them, it should be the same. But for the parallel inductors, that the current, it should be split or divided over them. So for example, if I ask you to distribute the current within this electrical circuit, so you're gonna draw an electrical current I, and this I is gonna keep moving or rotating through the electrical circuit. It means that the same current will be still the same over all these electrical inductors. It means that all of them are in series. So for the series inductor, is gonna work like the resistor typically. Their equivalent inductance is gonna be the sum of their inductances. Like you're gonna sum L1 plus L2 plus L3. This is gonna give us the total equivalent inductance to these 3 inductors. Typically the same like the resistor. How about the in parallel is going to be as well like the resistors. So if we do have a current, this current, it will be split into like I1 and I2 and I3 into three currents, as we explained before in chapter 3 and in chapter 2. And since the current is going to be split or divided over them, it means that they already arranged it in parallel. It means that to calculate their equivalent is going to be typically the same as we did for the resistors. So it will be 1 over L1 plus 1 over L2 plus 1 over L3, exactly the same like the resistors. So as you can see that the capacitor, the thing that, or the electrical element, that its calculation of the equivalent capacitance is different. It is the opposite to the capacitors and the inductors and the resistors. And at the end, there is, in this table, I give you a summary of all of the expression that we considered before so far for these three different electrical elements. That the volt I, or the volt in terms of the current, for the resistor, it equals the I times the resistance. As you can see that the voltage is proportionally related to the current. For the capacitor, the voltage, it is the 1 over C times the integral of the current over the time plus V0, where this, it means that the voltage is proportionally related to the integral of the current for the case of the capacitor, and the inductor, it is, its voltage is proportionally related to the derivative of its current, or the current over the inductor, which is L divided by times di by dt. The current in terms of the volt is going to be the opposite. For the resistor is going to be the current V over R according to Ohm's law, the Decembers law. And for the capacitor, it will be the current, it will be dependent on the time derivative of the volt, which is going to be equal C times dV by dt. And the current for the inductor, it will be the integral of the volt. There should be like V of t here. There should be V of t, the integral of the volt over time plus I0. How about the power and the energy? The power, it should be I square R or V square over R. This is for the resistor. For the energy for the capacitor, it should be 1 over 2 CV square, and the energy of the inductor, it should be 1 over 2 Li square. It is recommended when you calculate for the previous example and the example that we demonstrated in the previous video, when you calculate the energy, to use this expression. It is preferred to not do integral of the power as we did before, right? You can do so, but you have to make sure of that you're dealing with the power term as a single term, right? Because when we plot the energy, we are not incorporating the integral limits, so this would be confusing, or it would result in some incorrect results. So it means that it is advised to use this expression for the energy for the capacitor as 1 over 2 CV square, or the inductor as 1 over 2 Li square. For in case that would have series resistors, so their equivalent, it should be the sum of the resistances. The same thing for the inductor, but for the capacitor, it's going to work like parallel. You're going to do the opposite. You're going to deal with the capacitor like they are like parallel resistors, for example. The parallel resistor, in case that you have just two resistors, their equivalent will be R1 times R2 over their sum, their multiplication divided by this sum. But for the capacitor, it's going to be just the sum of the capacitances. For the inductor, is going to be typically the same like the resistor, is going to be the multiplication of the inductances divided by their sum. For the case that you do have DC voltage or DC current over the resistor, it won't gonna affect, it's gonna give the same voltage or the same current. It means that we don't care. It means that the resistor kind of it is not affected, whatever the voltage is variable over time or constant over time. The same thing for the current. It doesn't matter for the resistor, but for the capacitor, in case that the capacitor has DC voltage, it means that the voltage is constant, so there will not be any current through the capacitor. It means that the capacitor is gonna work like an open switch. It's gonna be like open circuit. But for the case that for the inductor, in case that the voltage, the current over the inductor is constant, it means that in case that we have DC current, so there will be no voltage over generated or no energy drop, or there is no energy generated by the inductor. It means that we're going to end up with a short circuit. So open circuit, when the capacitor will be open circuit, simply when the capacitor is DC voltage, or the volt is constant over the capacitor. But in case that the inductor will be short circuit, in case that the current is the one that is constant. Make sense? So these are the different properties of these different electrical elements, and this is going to be the end of the chapter 3. The next meeting we're going to discuss chapter 4. We're going to start chapter 4, and we're going to see how we can do electrical analysis or circuit analysis to electrical circuit that include all of these 3 electrical elements at once. Some electrical circuit that would include resistors or capacitors or inductors, or all of them together. We're gonna know how we can do analysis to this electrical circuit through chapter 4, and we're gonna discuss the transient, which is the main topic of this chapter. All right, so that's it for this chapter, and that's it for today's video, and thank you, and see you in the next meeting.